Hi, welcome to the next video about minerals, about mineralogy. This time I would like to continue what I told you in my first video about minerals. What is a mineral? If you remember, I told you that a mineral is basically a natural crystal, a crystal that is formed in the nature, by nature, that is without human intention. And today I want to concentrate a little bit more on what is a crystal actually. So the title of this third video is not by chance, by accident. Crystal is a term that is used both and found both in mineralogy and chemistry. So just to remind you, here I have our favorite alkanthites. And as you can see, you can believe me or not, but these are crystals. They're, however, tightly bound to each other. They're tightly intergrown. And this kind of a type of a look of a mineral, we say that it is a compact mass. However, if you look from this side, it's barely seen here, but the crystals that constitute this mass I showed you, this blue mass, are fibrous. They're fibers. So they're tightly intergrown fibers. And what I just showed you is a mineral, alkanthite, forming natural crystals. So mineral is a natural crystal. For a comparison, this is the bottom of a cup when I tried to make synthetic crystals of a synthetic counterpart or synthetic analog of this mineral. As you can see, the color is very similar. And these tiny elongated dots are actually quite larger crystals, which however are not a mineral but a synthetic. So these crystals are synthetic. Okay, but what is a crystal? So a crystal is actually a more physical chemical term because it is a description of a type of a solid. We know various solids, for instance, a paraffin or any kind of wax is not a crystal; it's amorphous. A crystal it's actually a situation when we take a group of atoms and we locate them very precisely in the crystalline part, so inside a crystal. And this very characteristic set of crystals, so both type of atoms so both of atoms, so this typical set of atoms and the way they're being set against each other, so the geometry, internal geometry, is enclosed in something that is called a unit cell. So you can imagine unit cell as an imaginary, for instance, a cube, an imaginary shape, and inside this shape there are atoms which are enough to compose a total crystal. How is it being done? So this unit cell, this, for instance, a cube or a rhomboid, it depends on the type of a crystal, is simply being copied. In terms of geometry, this copying of this unit cell is called translation. So we translate it and copy it. For instance, if this is say a shape of our unit cell that bears all the crystals, all the atoms we need, and also it contains a very characteristic set of the atoms. So how they are being placed against each other. We paste it and copy paste in one direction, second direction, and third direction. So X, Y, Z, until we touch what is called the face. And exactly, if you look at the crystal, both in a microscopic term, or if you use a binocular or any kind of a microscope, where you can see a shape of a crystal, then you are actually looking at crystal faces. And the way the crystal faces are being set against each other is not by chance. It's not by accident. It is related to what is happening in terms of geometry inside the crystal. if we describe a crystal macroscopically, so when we are talking about the crystal habits, so this is one of the physical features of minerals, but also crystals in general, a habit. Okay, so is it elongated? Is it or does it have a more rounded shape, or is it, for instance, a prism or a leaf or a lath, sorry, or a fiber? It will always be dependent on the geometry which is inside. However, if we are describing the outside of the crystal, then this kind of science is called crystallography, and it's being used especially in mineralogy, but also sometimes in chemistry. However, what is much more common now in both of these sciences is when we look actually at the interior of crystals. So basically, if you look at the crystal structure, this science is called crystal chemistry or crystallochemistry, and is again found in chemistry and mineralogy. What governs the shape of the crystals, and also what governs the characteristic sets of atoms that are being enclosed in this unit cell? Of course, symmetry, or being more precise, symmetry elements. What kind of elements of symmetry do we have? They are quite simple. It's quite a basic geometry actually, and it was already known by, for instance, Greek mathematicians who were able to foresee various shapes of crystals. So the first type of first major group of symmetry elements is actually containing a single element, which is called center of symmetry. Then there's a second group, quite a large group, which bears symmetry axis. What kind of axis, symmetry axis, do we know? So the first one is written as number 1, and it's usually called identity. How does such a symmetry element operates? So if this is our axis, and this is, for instance, an atom, then one or identity makes a rotation. This atom is being rotated back to his original place. So this is a rotation by 360 degrees. So actually nothing happens. This is why this element of symmetry is called identity. However, we can also call it an axis with a multiplicity of 1. Then there's, for instance, like this, an axis which might be an axis with a multiplicity of 2. So if we divide 360 degrees per 2, we get 180. So if here's an atom, then it's being rotated by 180 degrees. If the axis goes like this, then the atom will rotate like this and will be placed somewhere here. Okay. Then we have an axis which is written as 3. So if we divide 360 degrees by 3, we get 3 rotations, each by 120 degrees. Then we have an axis with a multiplicity of 4. So we have 4 rotations by 90 degrees. And finally, the most complex one, we can call it axis number 6. So with this axis, we have 6 rotations, each by 60 degrees. And it could be over. However, I told you about how a crystal is actually being constructed. So if we need this unit cell, and you can imagine this unit cell as a shape which imitates it's basically how to call it, a model. And we copy this model as I showed you in the X, Y, and Z direction. So this copying, fortunately, unfortunately, depending on what you like, induces some additional types of symmetry elements. This translation induces it. And if you compare some symbols that describe symmetry of crystals, and if you compare it from the crystallographic part or type, so the outer part, with the internal part, which is crystal chemistry or crystal chemical part, then you will see some differences. For instance, you will see a number 2, which would be symmetry axis with a multiplicity of 2. However, with the lowercase 1 in the lowercase. What does it mean? So this is a type of a screw axis. So if you take an axis again and an atom, what happens in the beginning is, of course, a rotation by 180 degrees. So we get the copy of the atom here. But this is not over. This lowercase 1 means that we need to translate the atom according to the in a parallel way to our axis, and by what kind of translation it is. So this 2 1 means that if we divide 1, so this lowercase, per the multiplicity of the axis, so 1 per 2, so this is exactly a part of this translation. Okay, so this 1 per 2 is being multiplied by a very specific, very specific for each type of crystal and compound. A very specific